I'm Nick.
I'm Jasmine. And I'm Kathleen. Today we're doing an experiment on friction!
Before we get into the experiment, we have to look at the content behind the experiment, which is, in this case, forces. Forces provide us with a way to explain how external influences can affect the movement or motion of an object. This theory was largely developed by Sir Isaac Newton back in the 17th century. His argument was that forces were the changes in an object's motion by an external force, rather than it actually being the object. He believed that an object would continue in a straight line at the same speed if there was no force acting upon it, or would just stand still and do nothing at all if it wasn't in motion. Forces act as an action and reaction pair. This means that if there is one force pulling forward, there will be an equal and opposite reaction pushing backwards. There are two types of forces, direct and indirect. These can also be known as contact and field forces, respectively. A direct force is a force that directly impacts a change in the movement of an object. These can be like using your foot to kick, stop, or change the direction of a ball. An indirect force is a force that is passively affecting things without ever making direct contact with the object. A good example of an indirect force is gravity. The Earth's gravitational pull pulls the objects towards the Earth. This causes objects to have weight and to fall.
The direct force we are looking at for this experiment is friction, a force that affects objects that move across a surface. Friction always works as an opposite reaction force, because friction works against a moving object.
There are 4 types of friction: static, sliding, rolling, and fluid.
The type of friction we are looking into for our experiment is rolling friction. Moving an object over a surface forms this friction. The amount of frictional force that is produced is dependent on the surface an object is traveling on. Friction is caused by irregularities in two surfaces catching on each other as they move. In theory, a rough surface with more irregularities should produce more friction than a smooth surface.
Our inquiry question is, how does a change in surface affect the distance travelled by a moving object? The aim of our experiment was to find out what surfaces have more friction acting on a toy car and which surfaces have less friction. The Akara content descriptor that links to our experiment is Science, Year 4, Science Understanding, Physical Sciences, ACSSU 076. Forces can be exerted by one object onto another through direct contact from a distance. The chosen elaboration is comparing and contrasting the effect of friction on different surfaces, such as tires and shoes on a range of surfaces. For our investigation, we used a container, a car, a book, a measuring tape, cling wrap, a rubber band, a woolen jumper, a notebook, and a pen. Now you're ready to go. The surfaces we tested were carpet, wool, rubber, cling wrap, laminated table, grass, gravel, cement, and bitumen. We predicted that on the different surfaces, the car would travel 17 centimeters on carpet, 12 centimeters on wool, 40 centimeters on rubber, 15 centimeters on cling wrap, 100 centimeters on a laminated table, 10 centimeters on grass, 25 centimeters on gravel, 70 centimeters on cement, and 30 centimeters on bitumen. Here is a table listing our results for all 3 tests and their averages. The averages were 46.5 centimetres for carpet, 51 centimetres for wool, 68.5 centimetres for rubber, 19.5 centimetres for cling wrap, 286 centimetres for laminated table, 5 centimetres for grass, 67.5 centimetres for gravel, 147.8 centimetres for cement, and 67 centimetres for bitumen. Here is the information from the 3 tests in a bar graph. As expected, when the car went further, the surface was smooth and had less irregularities for the car to push against, thus being affected less by friction, as shown by the laminated table and cement tests. On the tests where the surface contained more irregularities and was therefore more affected by friction, we found that the car travelled a significantly less distance. Our lowest recording was on grass with a mean of 5 centimetres. This was because there was too much friction acting on the car. With more weight to the car and more pulling force, the car could be able to move further. The more friction that affected the car, the more the car's path changed. For example, when testing the bitumen, the mean was 66 centimetres when measured in a straight line, but the car went slightly further than this measurement because it turned as it rolled. This is why we got varying results for the bitumen tests. This is the bar graph of all of the averages of our tests. Now let's compare them to the predictions. As shown by the bar graph, the majority of our predictions were significantly lower than the tests. Grass, on the other hand, gave the opposite results. We predicted that the grass test would allow the car to move further than it did, but the test average was only 5 centimetres.
The experiment was conducted by one person placing the car at the top of the ramp and releasing it, using the car's own gravitational pull to build its speed and send it across the surface. When the car came to a full stop, the distance between the bottom of the ramp and the car's front wheel was measured to see how far the car had travelled on each surface.
For this experiment, our constant was the ramp angle and the car. We measured the distance that the car travelled, and we changed the surface that the car moved on.
During this experiment, we encountered several issues. Firstly was a design flaw on our initial idea. This idea was to use a sling and rubber band system to propel the car.
However, this was very problematic as we adopted a fair testing principle to this experiment. A fair test is an experiment where there would only be one variable change, which, in this experiment, was our surfaces, and that the rest of the variables in our experiment had to be kept the same. This meant that trying to keep the same level of force exerted by the sling difficult to manage, and because of this, we decided to change the experiment structure, and instead use the gravitational force of the toy car to give it speed to travel over the various surfaces. This was achieved by using a soft-covered textbook as a ramp on top of a case.
But Nick, didn't we have an original idea for our ramp? One that involved a piece of MDF that was just too thick?
The original ramp we used caused the car to hit the ground head first. This caused the car to lose a lot of its momentum before it continued down the surface. By using the soft cover of the book, this allowed for the car to transition seamlessly as it went down the ramp onto the surface without losing any of the momentum it had gained by going down that ramp.
One of the problems during this experiment was trying to make sure the car would stay in a straight line, as some of our surfaces were narrow and we needed the car to stay on the surface, or in the case of the table, we needed the car to stay on the table until it came to a complete stop. This required a lot of tries and modifications. The tables were the only surface that proved the most problematic, as the toy went a fair distance and we had to put multiple tables together to compensate for the large distance the car would travel.
We tried to keep the angle of the ramp consistent with the use of iPhone's compass app, so that the change in ramp angle would not alter our results. The consistency of 39 degrees was achieved by altering the placement of the book on the container.
Students can witness friction in action in all activities they participate in. Some real-world examples of how objects move differently across varying surfaces may be connected to skateboards. Here we can see the rider gliding along the concrete surface smoothly, compared to a skateboard on gravel with more friction that comes to a complete stop. Another example students can experience for themselves is the different ways they can move across a wooden or tiled floor in socks compared to shoes. Other connections they could make could be bowling and ice skating.
An excellent example of friction is displayed when children ride their bikes. If they want to stop or slow down, they press the brake and the bicycle slows down because the friction between the brakes is moving in an opposite direction compared to the wheels. If we were to use this experiment in a classroom science lesson, we would recommend conducting the experiment on fewer surfaces. Also, the language used must be appropriate for the year level. This would mean that a Year 4 class conducting this experiment would not have to find the mean of their tests because this concept is not introduced until Year 7. We hope that you've enjoyed this short and insightful look into the world of friction and that many of you explore the numerous possibilities for engaging your students in the future.
Thanks for watching.